The question that I have is, could you do an example on a screw jack with square threads? In the theory video on this subject, we have considered a screw jack like shown in this picture and derived some equations, right? In doing so, we have idealized this problem into a simple sliding block type of model like shown in this picture right here, right? Capital T here is the torque applied at the collar level. W is the weight that is sitting on the shaft, including the weight of the shaft itself. The angle alpha is given by this equation where little l is the lead, that is the vertical distance between points 1 and 2, and r is the radius to the center line of the square thread, right? If the coefficient of friction of this contact surface is mu, like shown in this picture, the angle of friction phi is related to mu by this equation. We have considered 4 different cases, and the equations we have derived for these cases are listed here. The torque needed to lift the weight is given by this expression. The screw jack is self-locking if alpha is less than or equal to phi. If it is self-locking, then you have to apply a torque in the reverse direction in order to lower the weight, and that torque is given by this equation. When alpha is greater than phi, it is not self-locking, and when it's not self-locking, the screw is going to wind down on its own. You need to apply a torque in order to prevent the screw from winding down, and that torque is given by this expression. So instead of re-deriving these equations, I'm going to make use of them in solving some simple examples here. So here's our first problem. The lead is given, the radius to the center line of the thread is given, the coefficient of friction is given, torque needed to lift the weight is given, and we are supposed to find the weight that we are trying to lift here. This is the first case listed on the earlier slide, and the expression for torque is this. For this problem, in this equation, we know everything except the weight W. We just have to find the weight W. I also brought the equation for alpha and phi from the earlier slide. Here are my calculations. Using this equation, phi is calculated to be 16.7 degrees. Using this equation, alpha is calculated to be 1.824 degrees. Rearranging this equation, W is related to the torque and the other parameters by this equation, and substituting the numbers, we get 14.9 kilonewton for the weight. The details are pretty straightforward, so I'll let you follow. In a follow-up question, we want to find if this jack is self-locking. A screw jack is self-locking if alpha is less than or equal to phi, right? We've already calculated the values of alpha and phi over here, and it's pretty clear alpha is less than phi, and therefore the jack is self-locking. Referring to the same problem, problem number 3 is this. If the jack in part B is self-locking, determine the torque needed to wind it down. So we did determine that it's a self-locking jack, and therefore we need to apply a torque in order to wind it down. Just for reference, in problem 1, we had to lift the weight, right, and we had to apply the torque in this direction, right? This was the expression for torque in that case. But here in this problem, we have to lower the weight and we have to reverse the direction of the torque. And the expression for the torque is this. We already calculated values for alpha, phi, and W. The radius is given. Using these values in this expression, T star is calculated to be 79.2 Newton meter. Remember, we had to apply 100 Newton meter to lift the weight, right? So the calculation here tells us that we need to apply 79.2 Newton meter to lower the weight. Let's do one other problem. If L is 45 millimeters, everything else remaining, that means W is 40.9 kilonewton, R is 0.02 meters, and phi, the friction angle, is 16.7 degrees. The first part of this question is the screw jack self-locking? The second part is, if not, determine the torque needed to hold the jack from winding down. The first step of answering this question is to go ahead and calculate a value for alpha. And I got a value of 19.7 degrees for the lead of 45 millimeters. Since alpha, which is 19.7 degrees, is greater than phi, which is 16.7 degrees, the jack is no longer self-locking. From the theory video, we found out that when the jack is not self-locking, the torque needed to hold the jack down from winding down is this. T equals Rw times tan alpha minus phi. Using this equation, I get a value of 15.6 Newton meter for T, the torque. So this is the torque that needs to be applied in order to keep this screw from winding down on its own.